Now we'll be looking at properties of eigenvalues and eigenvectors. Please look at the previous slide for better understanding. We will solve few problems based on properties of eigenvalues and eigenvectors. Please like, share, and subscribe this particular channel. Let us start now with the properties of eigenvalues and eigenvectors. Okay. If you consider matrix, okay, A n cross n matrix, okay, the first property is nothing but sum of eigenvalues is equal to trace of A, which is equal to sum of diagonal elements of an A. If you consider matrix A, which is 2 cross 2 matrix, if you consider this particular matrix as 2 2 1 3, now you have to find the eigenvalues. Sum of the eigenvalues is equal to trace of A, right? So to find the eigenvalues is nothing but determinant of A minus lambda I, right? So it becomes 2 minus lambda 2 1 3 minus lambda. So find the determinant of this one. So it becomes 2 minus lambda 3 minus lambda minus 2 is equal to 0. So it becomes lambda square minus 5 lambda plus 6 minus 2 is equal to 0. So it becomes lambda square minus 5 lambda plus 4 is equal to 0. So we can write this one as lambda minus 1 and lambda minus 4 is equal to 0. So eigenvalues lambda is equal to 1 and 4 are the eigenvalues, right? Now sum of the eigenvalues is nothing but 1 plus 4, which is equal to trace of A is nothing but principal diagonal elements, sum of it, 2 plus 3. Yes or no? 1 plus 4 is 5, 2 plus 3 is equal to 5 in both the case. So sum of the eigenvalues is equal to trace of A, which is nothing but sum of diagonal elements of a matrix A. Okay, come to the second one. Product of eigenvalues is equal to determinant of an A. Okay, we have seen that the eigenvalues are 1 and 4. So product of them is nothing but 1 into 4, which is equal to 4. Now it should be equal to determinant of an A. What is determinant of A? Is nothing but we have to find the determinant of 2 to 1 3. Right. So it becomes 6 minus 2, which is equal to 4. So determinant of an A is 4. So you can see that product of eigenvalues is equal to nothing but determinant of an A. Now coming to the next one. All the eigenvalues are non-zero for non-singular matrix. What is a non-singular matrix? Is nothing but determinant of a matrix A should not be equal to 0. If you see the example, same thing, 2 to 1 3, you can see the determinant is 4. It's non-zero, right? So for non-singular matrix, so this particular matrix is non-singular matrix. So eigenvalues are non-zero. So we got the eigenvalues as 1 and 4 only. Come to next one. At least one eigenvalue is 0 for a singular matrix. What is a singular matrix? Is nothing but when determinant of a matrix A is equal to 0. Okay. So consider one example for this one also. Okay. Like 1 2 1 2. If you want to find the eigenvalues for this one, it becomes 1 minus lambda 2 1 2 minus lambda, right? So find the values for it. 1 minus lambda into 2 minus lambda minus 2 is equal to 0. So it becomes lambda square minus 3 lambda plus 2 minus 2 is equal to 0. So we get lambda square minus 3 lambda is equal to 0. Then we get lambda into lambda minus 3 is equal to 0. In this particular case, we got the eigenvalues as 0, 3. So in the case of singular matrix, means determinant of an A should be equal to 0. If you want to find the determinant of this one also, it becomes determinant of this particular matrix 2 minus 2, which is equal to 0. So it is a singular matrix. So one of the eigenvalue will be 0 in the case of a singular matrix. Now come to the next one. Eigenvalues of diagonal matrix or scalar matrix or triangular matrix are diagonal elements. Okay. What is a diagonal matrix? Is nothing but if you have some matrix as A 0 0 B is known as a diagonal matrix. We have only diagonal elements. Come to scalar matrix is nothing but if you have some values like P 0 0 and p. The diagonal elements are same and other terms are 0. It's another scalar matrix. Triangle matrix, we have two types. Upper triangular matrix like AB 0C is an upper triangle matrix. In case of a lower triangle matrix, we get as like X 0 Y Z is a lower triangular matrix, right? So for this one, the eigenvalues in the case of diagonal matrix, the eigenvalues lambda is equal to nothing but a comma b only. In the case of scalar matrix, the eigenvalues are p comma p only. Again, in the case of an upper triangle matrix, the eigenvalues are nothing but a comma c. And in case of lower triangle matrix, eigenvalues are nothing but x comma z. Okay. So whenever you take in a diagonal matrix or scalar matrix or triangular matrix, the eigenvalues are diagonal elements. Okay. Come to the next one. Eigenvalues of an unit matrix are always 1. If you consider an identity matrix, I is equal to 1 0 0 1. In this case, the eigenvalues are nothing but 1 comma 1 1. Okay. Come to the next one. Eigenvalues of an idempotent matrix A square is equal to AR, either 0, 1 or both 0 and 1. Okay. In the case of an idempotent matrix, it's not when A square is equal to A. Eigenvalues are 0, 1 or both 0 and 1. Come to the next one. Eigenvalues of an involuntary matrix A square is equal to I are either 0, minus 1 or both 0 and minus 1. Okay. In the case of an involuntary matrix, A square is equal to I. Come to the next one. Eigenvalues of an nilpotent matrix A power n is equal to 0 are all zeros. Okay. In case of a nilpotent matrix where A power n is equal to 0 are nothing but having a eigenvalues zeros. Come next one. Eigenvalues of an symmetric or Hamilton matrix are all real. What is a symmetric matrix? Is nothing but A is equal to A transpose. Right. What a Hamilton matrix is nothing but in the case of a complex number, we take a conjugate and take a transpose. So it becomes A conjugate whole transpose, which is represented as A power theta. Right. It's nothing but Hamilton matrix. Then a symmetric matrix. Right. Where A is equal to nothing but A transpose. Here A power theta is equal to A in the case of an Hamilton matrix. Then we get the eigenvalues as an real numbers. Okay. Come to the next one. In the case of an eigenvalues, in the case of an skew symmetric and skew Hamilton matrix, we get an eigenvalues as 0 or purely imaginary. What is a skew symmetric matrix? A is equal to minus A transpose. Right. What is a skew Hamilton matrix is nothing but A is equal to nothing but minus of A theta. In the case of complex number, we use an A theta, which is equal to nothing but conjugate transpose minus A conjugate transpose. As I know, we'll be looking at few more properties of eigenvalues and eigenvectors. More important properties of eigenvalues and eigenvectors. Okay, the first one is eigenvalues of orthogonal matrix A into A transpose is equal to I, or A inverse is equal to A transpose is nothing but eigenvalue would be 1. We can say that lambda can be plus or minus 1. Okay, eigenvalues. Okay, if you consider an example like A matrix is equal to something like 0 1 1 0. If you do the A transpose, then we get as 0 1 1 0 only. Yes or no? So it is nothing but if you multiply both of them, A into A transpose, we get as 1 0 0, which is equal to I. So it is an orthogonal matrix. We find the eigenvalue for it. Okay, eigenvalue is nothing but we have to find the value of a determinant of A minus lambda I. So it becomes nothing but minus lambda 1 1 minus lambda, which is equal to 0. Then it becomes lambda square minus 1 is equal to 0. So we get lambda value is equal to 1 comma 1. Yes or no? So in the case of orthogonal matrix, the eigenvalues will be mod of eigenvalue would be 1. It's nothing but eigenvalue would be plus or minus 1. Similarly, come to the second one. Sum of all columns or rows of a matrix is equal to one of the eigenvalue of symmetric matrix. Okay. For this one also I will give you an example. What is symmetric matrix? A is equal to A transpose. Yes or no? So if you consider matrix A is equal to something like 2 1 1 2. If you do A transpose, then we get 2 1 1 2 only. Yes or no? So find the eigenvalues of it. Is that my determinant of A minus lambda I is equal to 0, which is equal to nothing but equal to determinant of 2 minus lambda 1 1 2 minus lambda, right? So we get as 2 minus lambda whole square minus 1 is equal to 0, which implies it becomes lambda square minus 4 lambda plus 4 and minus 1, so it becomes plus 3 is equal to 0. We can write this one as lambda minus 3 and lambda minus 1 is equal to 0. So we get lambda is equal to nothing but 1 comma 3. We are saying that sum of all columns are rows of a matrix. Okay, if you add the row or column, okay, if you add the row here, it becomes 2 plus 1, which is equal to 3, and 1 plus 2, it is also 3. Similarly, the column 2 plus 1 or 1 plus 2, it is nothing but 3, which is nothing but an eigenvalue of a symmetric matrix. Okay, come to the next one. A and A transpose have the same eigenvalues but different eigenvectors. It's very important. Okay, A and A transpose have the same eigenvalues but it have a different eigenvectors. Okay, come to the next one. If lambda is an eigenvalue of a matrix A, then lambda square are eigenvalues of A square. Okay, and lambda cube are eigenvalues of A cube, and lambda power n are the eigenvalues of an A power n. Okay, and 1 by lambda is an eigenvalue of an A inverse, and determinant of A by lambda is an eigenvalue of an adjoint of an A. It's very important, this one. Okay, and come to the next one. Lambda plus or minus k into m is an eigenvalue of an A plus or minus k into I into m, where m and k are nothing but an k comma m are scalar values. Okay, they are scalar values. Okay, when you add with something and multiply with this one, then the matrix, it is equal to nothing but matrix add with some identity matrix, k into identity matrix, and with an m. Come to the next one. K into lambda is an eigenvalue of an k into a. Okay, come to the next one. Eigenvector corresponding to distinct eigenvalues are always linearly independent. Okay, if you have different eigenvalues, then eigenvectors are nothing but any linearly independent. Okay, few more important properties of eigenvalues and eigenvectors. The first one is for a matrix. Okay, A bar m, A inverse adjoint of A, and A plus or minus k I m have the same eigenvectors, but they would be different eigenvalues. Okay, but they would be having different eigenvalues, but they would be having the same even vectors. Okay, come next one. If x is an eigenvector of A, okay, then k into x is also an eigenvector of an A only. Okay, k is in a scalar value. If you multiply this one with x, then it is also an eigenvector of an A only. And you can say that from this, so eigenvalue lambda has infinite number of eigenvectors. Yes or no? If you have one eigenvalue, then it has infinite number of eigenvectors. As we can multiply k with an x, scalar value x, then it also an eigenvector of an A only. Okay, come to the next one. If an eigenvalue lambda is repeated m times, okay, then m is called as an algebraic multiplicity am, and corresponding number of linearly independent eigenvectors are called as a geometric multiplicity. Okay, and it is given that gm is less than or equal to am. Okay, this is very important. So we are talking here about the eigenvectors. It will be less than or equal to am. Am is nothing but eigen values. Come next one. lambda is an eigenvalue of an orthogonal matrix, then 1 by lambda is also an eigenvalue of same orthogonal matrix. Okay, as I know, as we know that in case of an orthogonal matrix, okay, determinant of an orthogonal matrix, okay, A is equal to plus or minus 1 will be getting. Yes or no? So we can say that if lambda is an eigenvalue of an orthogonal matrix, then 1 by lambda is also an eigenvalue of an same orthogonal matrix. Note points of an eigenvalues and eigenvectors. The first one is alternative method to find the eigenvalues of A3 cross 3 matrix is given as lambda cube minus lambda square trace of A plus lambda into sum of minus of A11, A22, A33 minus determinant of an A is equal to 0. Okay, this is a shortcut method to find the eigenvalues. Coming next one, if lambda is eigenvector, then x by mod of x is called normalized eigenvector or unit eigenvector. Okay, whenever they ask in a question about the normalized eigenvector or unit eigenvector, then you have to divide x by mod of x. Okay, coming next one, if there are m times repeated eigenvalues lambda, then the corresponding number of linearly independent eigenvectors is n minus r. Okay, where n is nothing but order of a matrix and r is nothing but a rank of an A minus lambda times of an I matrix. Okay, you have to remember this one. I'll be solving few problems on this one also. Okay, this is a basic thing you have to remember to solve a problem very easily. We're solving few problems on eigenvalues and eigenvectors. Now based on properties, we'll be solving few problems. Okay, the first one is eigenvalues of a skew symmetric matrix. We know that it will be 0 or imaginary. So option C, either 0 or purely imaginary. Coming into next question. We have to match the columns 1 and 2. As an first one, singular matrix. Singular matrix is nothing but they are talking about determinant. Determinant should be 0. So it comes with an option 3. P is nothing but 3. Non-square matrix. If you consider a non-square matrix, it may have 2 rows, right? Like 4, 7. 2 rows and 3 columns. Also, a column is a non-square matrix, right? In this case, determinant cannot be defined. Option 1. So Q is 1. Unreal symmetric matrix. Okay. Uh, Coming to eigenvalues. Okay. Eigenvalues are always real. Option 4. R is 4. Right. Orthogonal matrix. Orthogonal matrix determinant is always 1. Okay. It's option 2. Right. So matching with is option A. Question. The question is eigenvalues and corresponding eigenvectors of 2 cross 2 matrix is given by the eigenvalues lambda 1 and lambda 2 given as 8 and 4 and eigenvectors v1 and v2 given as 1 1 1 minus 1. The matrices. You have to find out which of the matrix would be satisfied with respect to eigenvalues and eigenvectors. For this one, we know the simple one thing, right? Trace of a matrix A is equal to sum of eigenvalues. Yes or no? We know this one, right? So what is the trace of a matrix A is nothing but sum of the diagonal elements, right? If you consider matrix A, it is 6 plus 6, which is equal to 12, right? If you consider B, it is 4 plus 4, which is equal to 8. If you consider C, it is 2 plus 2, which is equal to 4. And if you consider this one, it is an 4 plus 4, which is equal to 8. What is sum of the eigenvalues we got at? Is nothing but 8 plus 4. Yes or no? Lambda 1 and lambda 2, which is equal to 2. So which of the options satisfy is nothing but option A. So answer is option A. A simple thing, right? If you want to solve it, okay, with this particular matrix, A matrix is given as 6 2 2 6, and the eigenvalues are given as 4 and 8. Yes or no? And we have to find the eigenvectors. Eigenvectors are given as A minus lambda I into x is equal to 0. So just substitute it. We get as 6 minus, consider this one first 4 term, okay, when lambda is equal to 4, 4 2 2 6 minus 4, so it becomes nothing but 2 2 2 2, yes or no, and you multiply with an x, so we get as 2 2 2 2 with an x. So if you consider x values as an, consider x value as an x and y, then become x and y is equal to 0. Then we can say 2x plus 2y is equal to 0. Another one is 2x plus 2y is equal to 0. From here we can say that x is equal to nothing but minus 1. Yes or no? So when lambda is equal to 4, then x is equal to minus 5. If x is equal to 1, then y is equal to minus 1. This one got satisfied. Now coming to when lambda is equal to 8, then it becomes this particular matrix would be changing to 6 minus 8, 2, 2, 6 minus 8, right? So which is equal to nothing but it becomes minus 2, 2, 2 minus 2. Yes or no? Now we have to subtract with an a, multiply with an x. So it becomes minus 2, 2, 2 minus 2 with an a, x and y. Yes or no? So here it becomes nothing but minus 2x plus 2y is equal to 0. Another one is 2x minus 2y is equal to 0. Then we can say x is equal to y. When x is equal to 1, y is equal to 1. So when eigenvalue is 8, so it got satisfied. This is the answer. Okay, the simple way is nothing but just check the trace of an A. Next question. The question is we're defining the eigenvalues by using a shortcut method. Okay, now in this particular question they are asking to find the eigenvalues, right? Now we'll be using this particular formula to find the eigenvalues, right? So it is given as lambda cube, so it is in a lambda cube minus lambda square into trace of an A. What is in trace of an A? E. It is equal to nothing but sum of the principal diagonal elements. So it becomes 8 plus 7 plus 3, which is equal to nothing but 18, right? So it is 18 plus lambda times of an A, sum of the minus of an A11, A22 and A33 is nothing but defining one by one. What is A11? It is 8, right? So minor of it, we're defining it out. A11, we got the value as nothing but we have the determinant of, if you remove the A11, the row and the column will be removing it. Then we get in a 2 cross 2 matrix. It is given as 7 minus 4 minus 4, 3. Right? Now coming to A22. It is an A22, right? Now we'll be removing the row and the column. So the remaining elements are 8, 2, 2, 3. Right? Again coming to A33. A33 is nothing but 3, right? So we'll be removing the row and the column. The other elements are nothing but 8 minus 6 minus 6, 7, right? Now defining the determinant of each one of it. So it becomes 7 into 3 minus minus of minus. It becomes 4 into 4, right? 7 into 3, 21 minus 16, right? It becomes 5. Again find this particular value. It comes 8 3 is 24 minus 2 to the 4, which is equal to 20. Again here it becomes 8 7 is 56 minus 36, which is equal to 20. So it will be adding all of them. It becomes 5 plus 20 plus 20, right? And minus determinant of an A, we have to find it out. Find the determinant of this particular matrix. Determinant of an A is equal to, the first term is 8, 8 into 7 3s are 21 minus 4 4s are 16. Minus minus get cancelled and becomes plus. 6 into 6 3s are 18 becomes minus 18, and here it becomes plus 8 plus 2 times of an, here 6 4s are 24 minus 7 2s are 14, right? So it becomes 8 into 5 plus 6 into minus 10 plus 2 into 10, right? So 8 5s are 40 minus 16 plus 20, which is equal to 0. So we got the value as an 0 is equal to 0, right? So we get lambda cube minus 18 lambda square plus the sum of this one is nothing but 45. 45 lambda is equal to 0. If you consider lambda common term, then it becomes lambda square minus 18 lambda plus 45 is equal to 0. This term we can write in the form of lambda into lambda minus 15 and lambda minus 3 is equal to 0. So lambda is equal to nothing but as 0, 15 and 3. These are the eigenvalues by using an alternative method or shortcut method to find the eigenvalues. Okay. Now come to the next question. It is based on normalized eigenvector or unit eigenvector. Okay. Matrix is given here. You have to find the normalized eigenvector. Right. So for this one, to find the eigenvector, first we have to find the eigenvalues. Right. So how to find the eigenvalues? We know that is nothing but a minus lambda I. Determinant should be equal to 0. Right. So a matrix is given here. So if you write in this particular format, so it becomes 5 minus lambda 3 1 and 3 minus lambda. You have to find the determinant of this one. So it becomes 5 minus lambda into 3 minus lambda minus 3, which is equal to lambda square minus 8 lambda plus 15 minus 3, which is equal to lambda square minus 8 lambda plus 2. We can write this one as nothing but lambda minus 2 and lambda minus 6, right? So which is equal to lambda is equal to 2 or 6. Yes or no? So we got the eigenvalues. Now we have to find the eigenvector. Case 1 when lambda is equal to 2. Okay. Case 1 when lambda is equal to 2. Just substitute in this particular matrix. So it becomes 5 minus 2. It is 3 and it is 3. It is 1. 3 minus 2. It is 1. Right. Now we have to find the eigenvectors. The general thing we know for eigenvectors is nothing but determinant of A minus lambda I with an X matrix is equal to 0. Yes or no? So just substitute it. We get nothing but 3, 3, 1, 1 with an X matrix. There's nothing but if you consider X and Y, yeah, is equal to 0. Then you get 3x plus 3y is equal to 0. And x plus y is equal to 0. That means x is equal to nothing but minus y. That is nothing but if x is equal to 1, then y is equal to minus 1. So we got an x matrix which is equal to 1 and minus 1. Now you have to find the normalized value of it. It is defined as x by modulus of an x, right? So it becomes normalized value of an x. It becomes x by modulus of an x, right? So it becomes modulus of x nothing but we're taking in a square root of x square plus y square, which is equal to nothing but it becomes 1 plus 1, which is equal to root 2. So it becomes nothing but X matrix 1 by root 2 and 1 minus 1. Which of them satisfy option B, right? If you go with the case 2, okay. Case 2, when lambda is equal to 6. So just substitute the values here. You get 5 minus 6, it becomes minus 1. This is 3, this is 1, and 3 minus 6, it becomes minus 3, right? So you have to multiply this one, x and y should be equal to 0, right? So we get two equations, minus x plus 3y is equal to 0, and x minus 3y is equal to 0, which implies x is equal to 3y. When x is equal to 1, then y is equal to nothing but 3. Yes or no? If you find the modulus of it, modulus of x, it becomes under root of x square plus y square. So it becomes 1 plus 3 square, which is equal to root 10, right? But such option is not here, so we'll be going with option B only. Now coming to next question. The question is number of linear independent eigenvectors. Okay, here the formula is nothing but, we know that n minus r, right? So here n is nothing but an order of a matrix. It is given as 2 cross 2 matrix. So order of a matrix is nothing but n is 2 minus rank. You have to find the rank of an A minus lambda, right? So to find the rank of this particular value, first you have to know the lambda value. Here the matrix A is given as 2, 1, 0, 2, right? Now you have to find the value of lambda is how much. You can see that there is nothing but upper triangular matrix, right? Triangular matrix, right? So lambda is nothing but diagonal elements 2, 2. So we have 2 times repeated eigen values. So if you consider lambda is equal to 2, okay. Now if you substitute it A minus lambda I, then it becomes 2 minus 2, 1, 0, 2 minus 2, which is equal to 0, 1, 0, 0, right? So it becomes a row matrix 0 and 1, right? So the rank of an A minus lambda I is equal to 1. So we got the rank. So it becomes 2 minus 1, which is equal to 1. So number of linear independent eigenvectors is equal to 1. Answer is 1.